Hello all, welcome. We're going to talk, as Graham has suggested, about both the new Lingo and the Urika 2. I'll get right to it. I'm going to talk about some of the high-level messages and also what's going on technically, and Murray and I will be interchanging to discuss some of the more details of different aspects of it as well. So first up, we're going to do the new Lingo. We'll go through some of that. We'll then move on to the Urika, go through that, and then have a chance for questions. If you have any questions through any of this process, by all means, type them in. We've got some that have already been sent through, but type them in and we'll do our best to answer them at the end. So here we go with the Lingo, the new Lingo. It's a picture of it right there. To comprehend what it is, there's both a power supply and also the motor controller. You really think actually about the new Lingo as originally it would have been described as a power supply, but the Lingo has evolved quite a bit now to encompass both a power supply, a motor, and also, most importantly, with the new Lingo, the Lingo 4, a motor controller system, and we'll be talking about that at some length. And that's, in fact, the board that you can see on the screen there is the motor controller system. So what's new? It's our highest performance Lingo. It's our 4th generation Lingo. And if you think back to Ivor's original insight of the single point bearing, the whole point of a turntable, what you got to do at the turntable is to spin the platter more accurately and consistently. And the single point bearing introduced that to the market. Well, the next most important thing after the bearing is going to be the combination of the motor and the motor controller. And that's exactly what Lingo is seeking to do, has always been, and really takes to a new level now. So it's based on some technology from the radical design, in specific, the ability to sense the rotational speed of the platter itself, and then to be able to do that in a more accurate and consistent way. So we'll talk a little bit about this, both how the motor is being driven in a more, the motor and then the platter driven in a more accurate way, and then thanks to the tachometer that's inherited from the radical design, the ability to correct for that and to make it a more consistent approach as well. So number one thing to remember about the new Lingo is it spins the platter more accurately and consistently. The second thing to remember is that it has and it facilitates a far more precise and self-calibrating setup than the previous generations. We'll all remember, I'll talk about that in a little bit as well. Let's go to the first of those points. So accurate and consistent speeds. As best we could do in all the previous Lingos, they took the signals that they would drive the actual motor with from the mains. And so they would do their best to provide an accurate set of sine waves to drive the motor, but they would never be perfect. And what we're able to do is get much closer to perfection with the new Lingo. And the way that that works is we've integrated a lot of our expertise from FPGA design and D2A and amplifiers to actually generate a digitally perfect sine wave in an FPGA on that board that you saw at the beginning of the presentation. That's then passed through to an audio grade D2A and amplified to send actually the 2 sets of phases of the motor drive signal. So the first out of these 2 things you can recognize right away is that the motor will be being driven more accurately than it has ever been driven before. Then the third thing is that we're able to connect that in a feedback loop. And just like in the radical, we can sense the rotational speed, and the tachometer will ensure consistency by feeding that information back to the FPGA, where we're able to digitally adjust the wave and the signal that we're sending. And that has a number of effects, most specifically the accurate and consistent speed. The second consequence of that is that the precision and the ease of use of the self-calibration is far better than the past. We'll all remember needing to adjust the actual motor in order to change the speed. You had to adjust the angle that the motor was fitted with respect to the turntable. That was the only way that we could do speed control. Well, now, since the speed is actually being generated from a digital signal, and since we're getting feedback information about how it's actually running, all of that is fixed, and I'll go through that. So the results are that there's no mechanical adjustment of that motor required, and that has a knock-on effect as well, that the motor itself can be mounted in the most ideal form, which is at 90 degrees to the rest of the platter and the turntable. So I've got on the screen now a block diagram to describe this in a little bit more technical terms. And you can see in the sort of center left of that is an FPGA. And that FPGA I've described, it generates the digital set of 2 sets of sine waves that are taken digitally to the D2A and then through the amplifier. That will then be driven into the motor, and the motor will do its work, driving the platter. We're doing that at, again, a more accurate level than we would have previously been doing. And then the tachometer is sensing the speed of that platter and feeding that information back into the FPGA. the FPGA is then able to change the digitally driven signal to adjust for the feedback information it's getting from the tachometer. And of course, the way that 33 and 45 are handled here is that that button can switch between it, and the FPGA will generate the appropriate drive signals in both of those cases. The flash memory is there, that there will be a self-calibration point where the turntable will reach exactly 33 or exactly 45, 33 and a third or 45, and it will remember between power on and power off the precise setup for that table. So it's bespoke and specific to that customer's setup once it's up and running, which means it starts running at 33 and a third or at 45 right when you start it up. I'm now going to hand over to Murray, who's going to talk through some of the measurements we've made, both of the existing Lingo and then also the new ones, to demonstrate the precision engineering in what it is that we have been up to. Murray.
Okay. So the first picture I'd like to show you is a plot of the motor drive signal generated by the current Lingo 3. The vertical axis in the graph is voltage, and the horizontal axis is time. So the Lingo 3 drives a synchronous AC motor. So the ideal drive signal for such a motor would be two perfectly shaped sine waves offset in phase by 90 degrees. And as we can see by this picture, the Lingo 3 motor signal is good, but it's still far from perfect. We're now looking at the same Lingo 3 motor signal, but now in the frequency domain. The horizontal axis is now frequency, and the vertical axis is signal magnitude. A perfect sine wave would have just one single line at the motor drive frequency of 50 Hz. We can see that there is a line at 50 Hz, but there are also multiple lines at higher frequencies, 100, 150, 200, and so on. These harmonic products are caused by the waveform distortion that we saw in the previous graph. Why does this matter? It's only a motor after all. Well, these harmonics cause unwanted movement and vibration within the motor, and some of that vibration will inevitably be transmitted to the turntable platen. Also, if we look closely, we can also see small sidebands either side of the 50 Hz tone. These indicate that the frequency is not stable, but rather it's being modulated. And if the motor drive frequency is not stable, the motor speed will not be stable. So this is now the drive signal from the new Lingo 4. The Lingo 4 also drives the synchronous AC motor, but the motor has been redesigned to operate at a much lower voltage. In the Lingo 4, the sine waves are synthesized digitally within an FPGA, converted to analog by an audio quality DAC, and amplified by two Class A amplifiers. The result, as you can see, is two perfect sine waves with no visible signs of distortion. So this is the Lingo 4 signal in the frequency domain. We are now much closer to our single line at 50 Hz. Harmonic products are much, much lower, indeed lower than many audio amplifiers. Sidebands are only just visible above the noise floor, indicating that there is very little frequency modulation. So vibration within the motor will be reduced, and motor speed will be more consistent. And the final graph I have for you for the Lingo 4 is a measure of platter speed over time. The Lingo 3 is shown here in red, and the Lingo 4 in blue. The ideal case here would be a perfectly straight line at 33 1/3 RPM. You can see that the Lingo 3 speed drifts over time due to temperature variations in the drive electronics. The Lingo 4, because it constantly monitors the actual rotation speed of the platter, is able to maintain an accurate speed indefinitely.
Okay, thank you very much, Murray. So in summary, the new Lingo 4 is our best performance Lingo that we have had to date, and it's based on technology from the radical design. And in specific, the 2 points to remember when describing this to customers is that the platter spins more accurately and consistently. Accurately because the drive signal being given to it is more precise, and consistently because the tachometer and the feedback system allows that to work, as Murray just described, indefinitely in the way that it approaches its accurateness. And the second thing is that it has a precise self-calibrating setup. No more need to adjust the relationship between the motor angle and the rest of the setup in order to adjust speed. And it will remember that as well between turn-ons of the turntable. So that brings us to the conclusion of the Lingo section. I'm now going to move over and we'll talk about the Urika 2, and then there'll be questions, as I said, for both Lingo and the Urika 2 at the end of that section. So for the Urika 2, a picture to start. That is a close-up of the Urika 2. You will have seen some of this. There's also a Urika 2 onto the baseboard and also the cables coming out of it. So what is it? What's new? It is unquestionably our best ever phono stage. And there are 4 reasons for that. The first is it has our most precise implementation of the RIA or the RIAA curve that you'll find. The second is that the general philosophy has been to digitize and protect the signal from the earliest possible points, to take the ideas of the Urika 1, where we brought the amplification of the very delicate signal in as close as we could to the turntable, but actually to as closely as we could to digitize that. And some people might characterize this as some kind of analog versus digital discussion or war, and it's just nothing can be further from the truth. Linn's interest is in finding the best way across all of these different systems in order to best protect the signal. So in reality, this is actually a hybrid approach between analog and digital, and I'll describe that in a little bit more detail in a second. But the general philosophy has been to digitize the signal from the earliest possible point and then protect it, and that will have some other knock-on positive effects as well. So point 3 is, as I said, it's a hybrid design, so it is not a pure analog, it's not a pure digital solution, but there are still analog components. And anywhere there are analog components, there will be tolerances in those components. But thanks to the design and integrated manufacturing approach here in Glasgow at the factory, we're able to measure the specific tolerances of each individual Urika, and ensure that we can correct for those for each particular Urika and their customer. And the final 4th point is you can now digitally and flexibly do cartridge optimization in a way that wasn't possible with the Urika 1. So you can adjust the cartridge loading settings both for a number, quite a varied number of cartridges that we have support for, including all of Linn's recent and historic ones, and also cartridges from lots of other vendors. There's the ability to sit down in the listening position, in fact, and change those settings without needing to get out of the seats in a way that you can hear the impacts of it immediately. Okay, go on to a little bit more about this, about the product setup. To be absolutely clear, the Urika 2 connects over exact link, but it does not require an exact system. It's an important distinction. We've never talked about this a lot, but exact link was designed from the very beginning both to carry data towards speakers and also to carry data into the DS or DSM. So to give the terms, the ports a better terminology, exact link ports on a DS or DSM are actually what we refer to as exact link master out ports. And you connect a master out port, in the case of a Urika 2, to the slave in port of the Urika 2. And what that means is that the clock will be generated from the DS or DSM and given to the Urika 2, so the DS and DSM are in charge of the aggregate system. And then the Urika 2 provides the lossless data over exact link back to the DS and DSM. So the most straightforward way to connect a Urika 2 with Linn DS is exactly as what's on the screen here, by connecting the master out to the slave in of the Urika 2. What happens to that data then is that you use the benefits of your DS and DSM, of your catalyst-based the catalyst-based DAC architecture that we have in there, to generate the analog signal from that and go out through a standard passive system, left-right, for a stereo setup. So it does not require an exact system, although it does use exact link to do it. To be clear though, Urika 2 can of course work with an exact system. It's not required, but it does work and interoperate with an exact system. And in this case, you can connect it in a number of different ways. The Urika 2 could plug into the master out port as is showing on the left picture here. And then one speaker connects to the other master out, and then you can daisy chain from the Urika 2 to the other exact speaker. Similarly, you could hook it up so both speakers are connected to the master out, and the slave out from one of the exact speakers is sent, or the exact box for that matter, is sent to the Urika 2's slave in. It really depends on what the best setup is in the home for you in terms of physical locations. There is no consequence to the audio whatsoever. It is losslessly protected regardless of the daisy chaining scenario. And just to be completely, to cover all of the different cases here, this is a case where we daisy chain one exact speaker to the other, or an exact box to the other, and directly connect the Urika 2 with no further daisy chaining. So that is all of the product setup options for Urika 2. I'm now going to hand over to Murray, who's going to talk through both what the purpose of a phonostage is in general, how the Urika 1 went about implementing that, and the differences in a Urika 2. Murray.
So this is a simple block diagram of a typical phonostage. Phonostage has 4 basic jobs to do. Firstly, it must apply a suitable load impedance to the cartridge coil. This is important as it damps the high-frequency resonant circuit that would otherwise be formed by the cartridge coil inductance and the capacitance of the T-cable. Next, it needs to amplify the tiny signal generated by the cartridge. Then, it needs to reverse the equalization applied during the recording process. In other words, the RIAA curve. So, as I'm sure you all know, when vinyl records are cut, low frequencies are attenuated to prevent excessive groove modulation, and high frequencies are boosted to improve the signal-to-noise ratio. So an inverse filter must therefore be applied during playback in order to restore the original tonal balance of the recording. Of course, any inaccuracies in this equalization filter will cause a tonal imbalance in the playback signal. The final stage is an additional filter to reduce unwanted subsonic noise from various mechanical sources within the turntable, otherwise known as the rumble filter. The rumble filter must have a steep slope in order to attenuate frequencies at or below arm resonance, while still passing audio signals above around 20 Hz. So this is a plot diagram of what goes on inside current Urika, Urika 1. You see on the left that the cartridge loading is fixed. When the Urika 1 was designed, the loading was optimized for our current best moving coil cartridge at the time, and there is no way to adjust that if you want to use a different cartridge. We have an analog gain stage, which also includes the high frequency portion of the RIAA curve. And then we have a second filter stage, which applies the low frequency parts of the RIAA curve, and then 2 further filter stages, which together are needed to implement the steep sloped rumble filter. So when we analysed the Urika 1, we identified 4 potential areas of loss. Firstly, the cartridge load is always suboptimal. The 4 stages of analog circuitry add noise and distortion. Manufacturing tolerances of the analog filter components reduce the accuracy of the RIAA curve. And finally, the analog cabling required to transfer the output signal to the preamp will be subject to noise and interference. So for Urika 2, we adopted a hybrid approach. Things that are best done in the analog domain have remained in the analog domain. So cartridge loading is a pure analog function, but we have now made it adjustable under digital control. This means that we can apply an optimized load for any moving coil cartridge. The gain stage also remains in the analog domain, although we have redesigned it for use in a hybrid system. The gain stage is still the dominant noise source, but we have reduced its gain such that its noise floor just dominates the noise floor of the ADC. We then make this gain up again in the digital domain, where we can do it without adding any distortion. It may seem counterintuitive, but reducing the gain of an amplifier improves its distortion performance. so we get a better overall result. Same noise floor, but lower distortion. The high frequency portion of the RIA curve also remains in the analog domain. Remember that high frequency signals are boosted during the cutting process, so attenuating these high frequencies in the analog domain reduces the amount of headroom we need in the ADC, and this in turn improves the analog, the signal to noise ratio of the conversion. The ADC itself is an improved version of the one used in the Climax DSM. Each channel now has 2 ADCs working in parallel to increase the signal to noise ratio. All signal processing within the ADC chips is bypassed, and we implement our own algorithms within the FPGA. With the signal now safely in the digital domain, we implement the low frequency portion of the RIA curve and the rumble filter using an extremely accurate digital filter engine. We are also able to digitally correct for any inaccuracies in the analog portion of the design, and I'll talk a bit more about that later on. Finally, our amplified and filtered and corrected signal is transported losslessly over exact link to the DS or DSM. So to summarize the improvements, we have a digitally adjustable cartridge load, a single optimized analog gain stage. We measure and correct for any remaining analog component tolerances, and we deliver the signal losslessly. So let's see what this means in terms of actual measured performance. This first graph shows the measured deviation from an ideal RIA curve for the Urika 1. So the vertical axis here shows deviation from the ideal curve, and the horizontal axis is frequency. The left channel is in blue, the right channel shown in red. So perfect RIA implementation would show here as a flat horizontal line. We can see that for this particular Urika 1, both channels deviate from the ideal curve above around 1 kHz. There are also differences at low frequencies between the left and right channels. These deviations and differences are the result of inaccuracies in the analog components used in the Urika 1. So this is the same graph, but for the Urika 2. We can see that the deviation is reduced. We're much closer to our ideal flat line, and left and right channels are almost indistinguishable. This level of performance is only achievable due to the unique way we're able to characterize the analog gain stage and apply digital correction filters. We can demonstrate the effectiveness of the correction algorithm by turning it off. The inaccuracies of the analog gain stage are now evident at higher frequencies. Low frequencies are still well matched, as this section of the RIA curve is implemented digitally. So what we do is measure the response of each individual Urika 2 in the factory and calculate a unique correction filter for each one. The correction algorithm gives us the consistency and accuracy that would be impossible to achieve in a purely analog system. So now I'll hand you back to Keith, who's going to talk us through some more performance measurements.
Okay, so Murray's gone through the RIA curve and the implementation, the precision of the implementation that's there. I'd now like to show some graphs that talk about the output of all this. And so the first of these is a graph that's going to show frequency along the horizontal, magnitude along the vertical. And we have on the top Urika 1, and obviously has an analog output. And on the bottom graph, we have Urika 2, which has a digital output. What we've done is we've overlaid 3 test tones, one at 100 Hertz, one at 1 kilohertz, and one at 10 kilohertz. And you can see an ideal graph here would be an extremely low noise floor and 3 peaks up to 0 dB of those individual tones. Now, of course, there's going to be some level of noise and some level of distortion, but we'd like to see that as small and as limited as possible. And you can see from the Urika 1 that there are harmonics that come out that are of a much more substantial magnitude of each of those tones than it is in the Urika 2. And so that shows on a like-for-like basis that the Urika 2 has a better harmonic distortion behavior than the Urika 1. But of course, you might say, just before I go to that, you might say, and you should say, that the Urika 1 and the Urika 2, you can't use them on their own. They have to be participants in a larger system in order to play the music. And in Urika 1, it would go into an analog preamp, such as the Climax Control, our best ever performance analog preamp. Or in the Urika 2, it of course needs to go into into some sort of DS, ideally a Climax DS with Catalyst. And so this next picture shows that scenario. So if you take the aggregate thing, and again, you play that back, not just through the Urika 1, but through Urika 1 plus a Climax Control, and also a Urika 2 through a Climax DS with Catalyst. And you can see actually that the Urika 1 through the Climax Control can't make that signal better. In fact, as good as the Climax Control is, it makes that signal worse. There's additional harmonic distortion, and in fact, the magnitude of the ones that are there increases as well. But if you look at the Urika 2 with the Climax DS and Catalyst, it's virtually indistinguishable from the previous graph. And that's because the Climax DS with Catalyst is virtually transparent with respect to the noise and the distortion coming out of Urika 2, as good as that is. And so to further emphasize that, here's a final picture that shows the output of the Urika 2, the digital output, and then directly below it, again the Urika 2, but through the Climax DS with Catalyst. And you can see that there's virtually no additional consequence to doing that, and that's because of the extremely high performance of the Climax DS with Catalyst. So to summarize, the Urika 2 is unquestionably our best ever phonostage. It has the most precise implementation of the RA-AA curve that we have ever done. The philosophy has been to digitize the signal and protect it from the earliest possible point, and we've been through that, how that occurs. It's a hybrid design, as we discussed, both analog and digital, but trying to drive the digital path as close to the source as we sensibly can in order to best protect the signal. Because it's a hybrid design, there is always an analog aspect to it, but we're able, because of the integrated approach here at Linn into the factory, to be able to measure those analog component tolerances and correct for them. Murray showed the consequences, the very positive consequences of that in the graphs that he showed earlier. And finally, it has a digitally selectable, flexible cartridge optimization, meaning that you can use it with any of Linn's top performing cartridges or cartridges from other manufacturers as well, and in any case, get the right settings for that. Right, it's now time to move to Q&A. We'd be very happy to take any questions that you may have that have been generated as a result of our webinar here. Please type them in and send them up. I've also got on my iPad here a number of questions that you've sent in or other people have collected in advance. So I'm going to invite Murray back on as well, and the two of us will try and get through these. So I'll read them out and pass them over to either Murray or to myself. We've got one here. The first question in is for Murray. Is the new motor for the Lingo different than from the old one? And if so, how are they different?
So the motor is the, the same type. It's an AC synchronous motor. It's mechanically identical. The only difference is that the windings have been redesigned to run at 12 volts instead of 110 volts. So moving to that lower voltage allows us to use high quality switch mode power supply and also low distortion Class A amplifier to drive the motor, which wouldn't have been possible.
Okay, we've had one that's, do you need an exact system to use a Urika 2? And it's very definitive, no, you do not require an exact system to use Urika 2. You do require a Climax DS or Accurate, or any DS for that matter, with exact link ports. Our recommendation would be to, of course, use Climax DS with Catalyst with Urika 2 to get the highest performance, but you do not need an exact system. That said, if you have an exact system, it works very well with that as well. And to be clear, the Urika 2 will collect the data, digitize it, pass it through the Climax DS and on, or the exact Climax exact DSM, onto exact speakers or exact box, and work compatibly in a very high performance with the exact system. It works in both no exact system, straight out of Climax DS or DSM, or also in an exact system if you have that. I got another question here. So what's the benefit of Urika 2 over connecting a Urika 1 into the Climax DSM A to D? Murray, I think you'd be good to take that one.
I think we've already demonstrated that the aggregate performance of the Urika 2 is a step ahead of the Urika 1. In particular, the ADC implementation in Urika 2 is different from the Climax DSM. So in the Climax DSM, we use a stereo ADC device, and that provides pretty good performance. But for Urika 2, we use the same chip but in a dual mono configuration. So we use one DAC chip for the left channel, one ADC chip for the left channel, one ADC chip for the right channel. And that gives us about 3 dB improvement in signal to noise ratio.
Okay. Another question here. Do you still need a DSM with Urika 2, or will a DS be sufficient? I can take that. So very interestingly, if a customer, the answer is you can use a DSM or a DS. They both work equally well if they have exact link ports on the back of them. And it provides a very interesting use case that if a customer is only interested in the turntable and network sources of music, then the DS actually becomes a preamp in that sense, and they can use a DS just for that. So they can have, if they have just a turntable and they have just network sources, then the Climax DS is a perfect solution for them. If they want additional inputs, then the Climax DSM is still the appropriate way to go, whether that's HDMI, SPDIF, or Toslink inputs, in addition to the Urika or the network source. So the next question that we have here is, what if my customer doesn't have a DS? What should I do? Well, I think the obvious answer to that would be to get them a Climax DS with Catalyst. It is by far, as we've illustrated on the graphs, the best way to, at a measurement level, and you can hear that in the DEMS as well, the best way to play back your turntable, to protect the signal coming out of the turntable, to digitize it, to protect it through to the Climax DS, and then use the benefits of Climax DS with Catalyst to play that back. Similarly, there's another question though, is this the only version of the Urika now? And to be very clear, the Urika 1 will remain in production, and that's for people who haven't made the move to DS yet, but they can continue to use the benefits of Urika 1 in an analog output. Our recommendation, of course, will be that they take a Urika 2 with the Climax DS. It is clearly superior, and you can hear that in the demonstrations as well. Another one here, I see that the Urika 2, and you would have seen this in the pictures at the beginning, has an optical output. What is the optical output for? The optical output is there for the purposes of recording, really, and that if you wish to make a recording of your vinyl, the best way that you could do that, without doubt, is to take the digital stream of the Urika 2 directly into your recording apparatus. And so the way that you would do that is you would connect your Urika 2 to a Climax DS or Climax DSM, and that would provide the aggregate machinery, so the clock would be provided from the Climax DS. The digital stream will be provided over ExactLink by the Urika 2, but it will also, that digital stream, be output over the optical output, the Toslink output. You can then connect that Toslink output into standard recording equipment, and you can make a extremely high precision recording of your vinyl, far better than would have been possible by any other system in the world will be possible there. So another question, why is there no analog output built into the Urika 2? The short answer for that is you can't fit a Climax DS up underneath the LP12. That is the output stage, the analog output stage. If you want the highest performance, a Urika 2 built into the turntable and a Climax DS transforming that digital signal into an analog one, that Climax DS we haven't surpassed as a way to convert into analog, and that remains so. It doesn't make sense to put that in under the turntable. It is what it is in the Climax DS with Catalyst. A couple other ones here. So a couple questions about ExactLink cables. Can I use a network switch to give me more exact ports? The answer to that is no. The ExactLink runs over the Cat5 Ethernet layer 2 standard, but it does not participate in Ethernet switching. Therefore, you can't plug it into an Ethernet switch. You can, to be clear, plug it into anything that has a direct electrical connection. So patch cables or patch ports that directly electrically connect to the other side are completely allowed, but not Ethernet switches or other things that engage in full Ethernet. And a related thing is what are the requirements and the lengths of Ethernet cables participating in ExactLink? And the answer to that is that they are the same as the Ethernet standard. So 100 meters is what's capable of typically being done. That is more than sufficient, I'd imagine, for the vast majority of living room setups for getting things to your speakers or to where the turntable for the Urika 2 may be. A couple other questions here. So does it support MM as well? Murray, do you want to take that relationship about the Urika of MM versus MC?
So just like the Urika 1, the Urika 2 has moving coil only. We take the view that to support both moving magnet and moving coil would compromise the design too much. We would have to have two switchable levels of gain and two different types of cartridge loading. So we take the view that it's a high performance system, and the majority of customers with those types of systems are most likely to have moving coil
cartridges. Okay. Final question here, and a couple more that have come in as we've been talking. So another one here, can I optimize for cartridges from other brands or only Linn cartridges? You can definitely optimize for a wide range of cartridges. We've got everything from the obvious ones from Linn, the Akiva, the Candid, the Clyde, the Crystal. There are others as well that are built in. These are selected in config, and so ones from Benz, from Denon, from Dynavector, from EMT, from Lyra are all there, and a number of them from Dynavector and others. It's also possible, if your cartridge of choice is not listed, to directly change the cartridge loading settings. And that's the basis of how we can improve the coverage of cartridges. There's quite a few already, but we're very happy to take feedback on other ones that are used commonly with it and to add them into config so that the sort of standard approach to a setting for that cartridge can be consumed inside of config. I think that answers those. I got a couple more. So next one, the question that's come in from the discussions here is, if you improve the filter for the IRAA curve, can this be updated via config? Murray, do you want to take that?
The IRAA curve is a fixed specified curve. But we could, because it is a digital system, we can implement other types of curves, and we are aware that there are some other recording curves out there. Currently, in the initial configuration, we only support the standard array curve. But if we get enough demand from customers or dealers, it would be relatively trivial to implement other types of curves as well in the future.
Okay, and so both that the Urika 2 turns into a software upgradable system is what Murray's getting at there. And so yes, both if there's further curves, that's an opportunity. Also, if there's improvements in the way that we actually match to any of these curves, we'll be able to software update into the Urika 2 to make that available to customers, just like we do with the DS or with Exact into the future. Okay, got another question here is, can you explain the drop-off in the curve below 100 Hertz and what's going on in the Urika 2? And that's due to the rumble filter, but I'll let Murray describe a little bit more in depth as to what's going on with that.
So those graphs that we showed measuring the deviation from the ideal RIA curve, the RIA specification doesn't include a rumble filter. So both Urika 1 and Urika 2 have rumble filters, so that's why they both have that drop-off at low frequencies. The Urika 2 rumble filter is slightly different from the Urika 1, and we did a bit of experimentation and listening to different types of rumble filter. Because we implemented digitally, it's very easy to switch between different types of rumble filter, different frequencies, different slopes. And the one we arrived at is slightly different than the Urika 1, so that's why that curve looks slightly different.
That's the description, and the difference between the two curves is because of the different rumble filter that's been applied.
Yes.
Yeah, so another question there, how does the cartridge optimization work? Is this digital? Murray talked a little bit about this before. It's digitally selectable, but it's implemented in an analog form. Do you want to speak a little bit more about that?
So just to be clear, the cartridge optimization is just an adjustment of the load, the electrical load that we apply to the cartridge as the signal enters the Urika. So we can only do that in the analog domain. These are passive analog components. And We do it in a similar way to the Euphoric, if you're familiar with that product. But instead of using manual dip switches on the underside of the product, we have digitally controlled precision relays that switch these different load components in and out of the circuit.
Okay, further question, can multiple Urika 2s be connected into a DS and a DSM? And the answer to that is yes. We support right now for 2 of them, and in theory that's expandable further, but we've implemented that for 2 right now. They'll show up as an exact link 1 and exact link 2 in your source menu, and you can select between them in that way.